Now, if I'm looking at this design in terms of factors, strictly speaking, it's three factors. I've got north versus south samples. I've got samples to this side of the map, to the west of the map, versus samples to the east of the map, and then I've got samples close to the source of the pollution and off to the side of the pollution. For the purposes of this video and some of the previous videos in the series, I'm just looking at this as a two-factor system, north versus south, and then with the other locations just specified as different locations. So I'm separating north and south, and then I'm just labelling these as 4 different locations, leaving out one factor just to simplify the situation. Okay, I've already imported the environmental and biological data into Primer in order to reduce the importance of the abundant taxa, so that the less abundant taxa have more of a role to play in the patterns that we see. I've taken the square roots of the abundances and then done the Bray-Curtis similarity calculation. And then if we do an MDS on that, we get a diagram, a coordination plot that looks like this. Now, it certainly looks as if there's some significant differences among locations, perhaps not, between north and south. And ANOSIM was one of the first methods developed to test for the significance of such differences. And it's based on calculations from the resemblance matrix. But it doesn't use the raw values, it uses the ranks of those values. So every value in here is converted to a rank from the smallest value, from the smallest percent similarity up to the largest, and then all the subsequent calculations are done on the ranked values. In other words, we lose information that comes from the actual magnitude of the differences. I'll come back to that a little later on. Now, actually running ANOSIM is simple if I have the factors already set up. So over here in the biological worksheet, I've got a blank column and then 2 columns which have the codes for the factors, and in this worksheet the samples are the rows. Okay, back to Primer. So it's simply analyse ANOSIM and then specify what type of design. So to start with, I'll just treat this as a one-factor design where I just want to compare the zones. So I'll specify the zone here, and I could include or exclude different levels. There's only 2 levels, so it doesn't make much sense fiddling with that particular option. And plot the histogram here. I usually turn that off, but I'll leave it on for this demonstration. Okay, go. Now, what ANOSIM does is it calculates a statistic called R. And R is scaled to range from -1 to +1. If the value calculated is +1, then there is perfect separation among the groups. If I go back to the MDS for a moment, there is fairly good separation among the groups here, but if we get looking at samples over the side here, we'll see that the samples are mixed up, so that not all of them are separating out. If each group was clearly distinct from the others, then the R value would be 1 or close to it. Significance is calculated by randomly shuffling the labels around. So go back to the MDS here. The north and south labels will be randomly shuffled or permutated around and a new R value calculated. So the histogram here shows the distribution of the randomized or permutated R values, and the dotted line shows the value calculated for the samples with their correct labels. I'll go back here. Here's the text results. First of all, we've got a summary up there, and then if we scroll down here, the global test statistics 0.14, which is indicating not much separation of the north and south groupings. There's a fair amount of mixing up there, but the test statistic is significant. It is 1.7%, which is less than the usual 5% level. What about if I run ANOSIM on not zone, but location? Here, I can choose to include or exclude particular groups. Okay, again, now you can see what's happening. The value is up here, 0.38. It's much greater than all the randomised values. And if we go to the test results and scroll down, 0.379, so that's modest. Significance level has dropped to 0.1%, so it's highly significant. And now, because we've got more than two groups, there are also pairwise tests in here. So west and far west are different, west and east are not, west and far east and far west, and east and far east are different, but far west and far east are not different. Note there is a negative number there, which indicates that an unusual situation where the samples are actually more interspersed than you would expect. So that's ANOSIM. Its strengths are that it's just working on the ranks. So the fact that there's an outlier over here, which might disturb the results of other tests such as MANOVA, is not an issue. That distance in there is not really going to come into account. Once we convert things to a rank, that will just be the furthest away from all the other samples. So that's the strength of the situation. It's also relatively easy to understand what's being done and to interpret. In the case of test for location, all these labels on here are just being randomly shuffled around and a new R value calculated. If we go and look at the two-factor ANOSIM, we also have to see some of the limitations. Now, I've been describing this as a two-way design, whereas strictly it should really be a three-way. But if we're looking at it as a two-factor, it's a two-factor with replicates, because there's replicate samples for each location and for north versus south. Again, I've got the same options down here. I'm just going to leave everything alone and run it. Oops, choose different factors for A and B. Well, I guess that would be a good idea. There we go. This time we'll take two graphs, one for the zone test and one for the location. Now the location, the line has crept up even further. It's up to nearly 0.7, because this test is now taking into account the fact that there are two factors in here, and the zone test has crept up too. Now the line is up 1.8. So the two one-way ANOSIMs were misleading. We go to the test here, scroll down. The test statistic for location, for zones. So it's tested between zones, north and south, 0.8, and the significance of that is 0.1%. Now, in fact, for both of these, the test statistic significance is 0.1%, simply because we ran 999 permutations, and the calculated test statistic for the real data was greater than all of those 99 permutations. If I actually go and run it again, but increase the number of permutations, back to the results, you'll see that the significance level drops even further. So I've got down to 0.01% for locations, because again, none of the permutated or randomized values was greater than the value for the real samples. It's not quite as strong for the north and south comparison. Again, because we've got 4 groups or 4 levels in the location factor, we've got pairwise tests and they give the same results as we saw earlier. Now, what is the main limitation here? The main limitation is that ANOSIM is unable to test for the interaction in the 2-factor design. In a crossed 2-factor design, as I have here, where all locations are present both north and south, there is a theoretical possibility of an interactive effect. And there may be some evidence for that in the graph here, in that the northeast are further away from the other samples than in the other grouping. So an interactive effect basically says that something complicated is going on, but ANOSIM is unable to test for that. It can only test for the 2 main effects. Per Manover, by contrast, I've done the per Manover. Per Manover for the 2-factor. The per Manover is able to test for the location effect. Now, per Manover actually gives quite similar results for the zone and location tests. Just as we saw for ANOSIM, but importantly, the per Manover is able to test for the interactive effect, and it's throwing up a interactive effect which is just as significant as the 2 main effects, and that is indicating that the locations are not showing the same results in the north and the south zone, or north and south region. And there's a very good reason for that. The pollution is coming from this spot here and this spot here, so it's going to be affecting those 2 areas greatly, and these areas out to the side hardly at all. But as the pollution spreads, its effect is going to drop off, and so the difference as we go across the map in the north is going to be much greater than as we go across the map down here towards the south. So there'll be modest effects of pollution here, here, slight effects there, strong effects here and here, little effect there and there. So in this situation, we would expect an interactive effect. The per Manover picks that up. It is evident in the graph, but the ANOSIM is unable to test for that, even though it does lead to correct conclusions about zone and location. On the other hand, the ANOSIM has the advantage that it is not going to be affected by outliers like this. In contrast, differences in dispersion within the groups can affect the outcome of per Manover. So if I was concerned about that here, I might actually exclude this particular sample point when I was doing further analysis. I hope that illustrates the use of 1 and 2-factor ANOSIM, and also describes some of the differences and similarities of ANOSIM and per Manover. Keith here. In this video I'm going to look at some of the options for the Manova in Primer. Now I'm not going to do them all. I'm going to do some of the ones people are most likely to look at and think about changing. And then in later videos I'll look at a couple of the others which require a bit more discussion to illustrate what they're on about. As I often do, I'm working with my simulated data because this allows me to create data sets to match and display particular things, particular points of interest. So you can see I've got two on the left, just 2 replicates per site versus 10 replicates in the map on the right. And to remind people of the scenario, if they have in previous videos, we're looking at a map of a marine environment with oil platforms which may be leaking oil to the environment. There is current from north to south, so if there's any oil leaking, it will spread southwards. That's why the replicates are downstream of the platforms. And the bottom goes from about 25 metres deep here to 75 metres deep here. And as we go down the depth gradient, the sediments get finer and have more nutrients. So here is the 2-factor file. I've got labels in the first column here that I can use to label the points on any maps or ordinations I draw in Primer. The X and Y coordinates there, the environmental variables, some summarised biological variables, and the actual biological variables across here. Different species of crustacea, mollusk, and worm. And these are counts of numbers of individuals in each of the replicate samples. And all of this data is invented and simulated, and I'm just going to use the biological data today. I'm not going to worry about the rest. Here exactly the same for the 10 replicate scenario, and if I scroll across to the side you can see I've got a blank column, and then I've got 2 columns with indicator or categorical variables for the factors. The first one is IVC, impact versus control, although I'm using the term REF now for reference, which is increasingly becoming used instead of control. Control is not quite right. We're really using these other sites as a reference for comparison to the potential impact. And then slope there is north versus south. Okay, here's Primer, and I've already imported both of those data files there, and I've selected just the biological variables. Now, before I do analysis, I could consider whether I should transform. So up here, if I go pre-treatment, transform, for this type of data, square root would probably be the choice, or possibly log x. But I'm just going to go untransform for this particular occasion. Oh, sorry, I'm going to go untransform, so I'll get rid of that. And what I need to do then is, of course, calculate the similarities. And for biological data, Ray Curtis is the default. This is just a warning to let me know that I haven't done any transformation, but that's okay, that's what I want. So now I'm going to do the Manova. To start with, I have to create the design. I don't know why I bother with this title, I don't think it turns up anywhere, but we'll put it in. Number of factors is going to be 2 here, as you saw in the Excel sheet. Double click gets me the first one, and there, I can switch to the second one. Neither of the factors nested, both are fixed. Now the last column over here, contrast, is interesting, and it's not something I've looked at before. It really needs a video on its own, but if I double click in here, what I can do is create particular contrast. Now the contrast will be between levels of the factor. Now in this particular design there's just 2 levels in each factor, so the analysis of variance is going to extract or test all of the relevant hypotheses, so contrasts are not really relevant here. If I had, for instance, included the 3rd platform, then I could by going down, clicking in here, set up a contrast between platform 1 and platform 2, for example, or platform 2 and 3, depending on how I wanted to look at that. But I'm not going to look at that any further. Back here, and here's the Firmanova options menu. So, first of all, the design worksheet is the only one that I've got made at the moment, design worksheet 1, so there's only one option in there. Over here, I don't have any covariables, or what we would call covariates in ordinary analysis of variance. I could, you know, you see it changed the sums of squares there. I'll get to that in a moment. I could have some of the environmental variables in a separate worksheet and use those as covariables. Okay, as you saw, when I put on covariables, it switched to type 1 or sequential, and I should also probably perhaps fiddle with the terms. So, what are we looking at here? Type 1 sums of squares means that the analysis is going to extract variation due to the different terms. So let's have a look at terms. We've got I, V, C, actually. Let's use the full names, so they're rather more informative. So that's what that one is. So it's sometimes convenient to turn that off so we get the full names. So the terms in the model are IVC, site pair, the two main effects, and then the interaction. So type 1 sums of squares, what it's going to do is extract variation due to either C first, and then site pair, and then IVC versus site pair. Now, because this analysis is balanced, and all combinations of the treatments are included, switching to type 1 sums of squares won't make any difference here. It would if I had a covariable, because variation due to the covariable is normally taken out first, and then we would look at these factors. But if the design is unbalanced, then we'll get different results with type 1 and type 3 sums of squares. Type 2, I'm not really going to talk about because they're not used very much at all. It's really type 1 versus type 3. Type 3 extracts the variation that's due to each of the terms. Again, it only makes a difference if the design is unbalanced. If the design is unbalanced, then some of the variation can actually be assigned to more than one term. And type 3 only extracts the variation that is uniquely due to that particular factor. If you have the Firmanova manual, this is very nicely explained on pages 69 and 70, particularly page 71 in the figure. Okay, buttons over here allows you to, for instance, change the order that the terms are, that the variation for the terms is extracted if we're using type 1 variation, and that's if we're using type 1 sums of squares. It also allows us to modify the model that's being used. So, for instance, if I am convinced there is no interactive effect, I can actually, just remove the whole lot. I can remove that one and just test for the main effects. Now, normally, we would just go with the model that Firmanova comes up with, because it's going to pick the model that is most appropriate to the design we've created. Pooling here means that I can add some sources of variation together. For instance, if I was convinced there was no interaction between site pair and IVC, I could pool those terms together. Reasons for doing this. The main reason for doing this is if there are limited degrees of freedom in a particular effect that's being used for creating an F-test. And by pooling terms together, we can increase degrees of freedom. That is the main reason. One other thing over here for the terms is that any term that is removed, that variation doesn't disappear. That variation ends up being pooled together with variation in the error term or residual term. So the video I did last week or the week before looking at ANOVA illustrates exactly that. Any source of variation that's not included in the model ends up in error. Okay, we'll come back to pairwise test in a minute. The permutation method. As in previous videos, I've just gone with the default because the defaults in ANOVA are generally the best. So for a factorial model, it will click usually this one here, the one that's second on the list. If you have a one-factor design, ANOVA will recommend you switch to the first option. So, according to the manual, the first option is a good approximate test which will have type 1 error close to alpha, although with larger sample sizes it tends to be more conservative. So with reps equal to 10, that option may tend to be conservative. But this method also does not need large sample sizes to work well, so it might be a better choice for the design with just 2 replicates. It's also computationally the fastest. It does suffer from problems if there happen to be outliers in covariables, so it would not be recommended in that case. For factorial, it's the default option because it has excellent empirical and theoretical properties, and empirically yields the best power and accurate type 1 error for multi-factor designs in the widest set of circumstances. So that's why it's the default. And that's why I would opt with this one most of the time. The last one. This method gives results highly comparable to method 2, but it relies on large within cell sample sizes for precision. So it might be okay with reps 10, but not with reps 2. It has the advantage of being faster for method 2, but on modern computers that's really not much of an issue unless you have a very large design with lots of factors, lots of variables. Okay, the number of permutations is an obvious one, and I'll come back to that. Short name we've already looked at. Fixed effects sum to 0. What many people will not be aware of is the fact that there are 2 ways of calculating the F ratios in analysis of variance. The option here, fixed effects sums to 0, is the one followed by many of the statistical textbooks written for the biological sciences. It's also referred to as the restricted model. In Minitab, which is a program I also use for doing analysis of variance, under the balanced ANOVA in versions up to version 16 of Minitab, under balanced ANOVA there is an option to use the restricted model. Turning this off gives us the unrestricted model, and it also calculates the F ratios in a way that is like the way used by SAS and some other major programs. Now, when does it make a difference? It only makes a difference for models which have some random factors. If all factors are fixed, turning this off and on should have no effect. If all factors are random, turning this on and off should have no effect. What it does mean is if you've got a 3-factor design or more, and there's 1 or 2 random factors, some of the F ratios will be calculated differently if this is turned off versus turned on. With it on, we'll get the same F ratios as using the restricted model in, say, Minitab, if the option is available for the particular design. With it off, we'll get the same results as Minitab's GLM, General Linear Model. In most of the areas where I practice, the choice is restricted model. Okay, so that covers everything. Here we go. Okay, so here's the Hermanova. First of all probabilities are less than 0.05, so there's a significant effect of all factors, IPC, site pair, and the interaction. But what I want to highlight over here is the unique Hertz. It's about 250, and that's the unique combinations that Primer Hermanova is able to find. And the reason it's relatively small is because there's only a number of replicants and only 4 groups in total. And that means when we get down here, the degrees of freedom for the test are quite tiny, 1 and 4, or as it's out there, 1 and 4. With about 250 unique Hertz, the smallest p-value we can get over here is 0.004. If the value calculated, the pseudo F, is bigger than all the permutated Fs, the value over here will be 0.004, and it can't possibly get any smaller. Now I'm just having a think about that, and what I'm going to do is increase the permutations. So that's one way of reducing that. But you see, it has no effect here because the analysis cannot find any permutations. Now, for this particular analysis, it's actually okay because, as I said, we can get a p-value down to 0.004. So these can be regarded as reasonably reliable. Let's go back and pairwise tests. Now, if the main effects in this analysis are significant, then I know impact differs from control and differs from south, and I just have to go and do the MDS plot to see exactly what's going on, or PCO. But the interaction is also significant, so to find out what's happening there,